The Burj Khalifa in Dubai is the tallest man-made feature on the face of the planet, and one of the greatest achievements in engineering history. To dream it up took outrageous ambition. To put it together requires nerves of steel. Constructing cranes taller, installing windows higher, and building bigger than ever before.
The immediate reaction was, are you crazy?
As the construction team makes history, they film it themselves. This is the story of one incredible skyscraper, and the people risking their reputations and their lives to build it.
All these people that are underneath this are at risk.
In the Middle Eastern Emirate of Dubai stands an architectural giant. At 828 meters high, the Burj Khalifa is the tallest building on Earth. This $1.5 billion tower opened in 2010 with one of the most spectacular fireworks displays ever seen. But this patch of land once looked very different. 6 years earlier, when construction started, it was little more than a barren, parched, and sun-baked desert. In February 2004, the team breaks ground at the Burj site. When you build this big, speed is of the essence.
Time is money. There's so much money invested in these buildings, you have to finish them and start recouping your investment.
Construction manager David Bradford is the man responsible for getting the job done on time.
So I was ecstatic, just to get a job like this. It's like a dream come true. This is the biggest building in the world. How many people get an opportunity to work on a job like this?
But as David starts work, the architects are still finalizing the tower's complex design.
The way you build a building like this, you have to fast-track it. So you can't wait until you get all the design in place. You'll be sitting there in your office for 3 years trying to get the design finished before you can tender it.
With large parts of the structure still on the drawing board, the construction team heads into the sky. The fastest way to build a tower like the Burj is with reinforced concrete, using a process called jump forming. The team builds molds at the base. They insert steel reinforcement bars and pour in concrete. Then when the concrete sets, the team lifts the molds up to the next level. And the process starts again. Using this system, the building begins growing at the pace of one new floor every week.
When you set the jump form up like this, you put the rebar in, you pour the concrete in the top. After 12 hours, this is 12 hours after you place the concrete, which is liquid, you pull the forms back and you actually climb the hydraulic jump form system up on the concrete that was previously poured. And then that climbs up automatically 4 meters at a time.
The Burj Khalifa is the brainchild of Dubai property developer Emaar. They want to proclaim the city's growing status as a global financial center by building the world's tallest tower. So Emaar has called in one of America's top architecture firms, Skidmore, Owings and Merrill. SOM is based in Chicago, the home of the skyscraper. As their chief engineer Bill Baker knows, building higher isn't simply a case of taking an old design and adding more floors. The added height creates a unique set of engineering challenges.
We're
We're on the 90th floor of the Willis Tower, formerly known as the Sears Tower. As you look out across Chicago skyline, you see almost a sampler of skyscraper technology. Over here is the Aon Tower, which was formerly called the Standard Oil Building, and it's a single tube.
Each time architects go taller, they must invent new structural systems.
If you look, the predecessor to the Sears Tower, the John Hancock Tower, it's called a brace tube. So you can see the diagonal bracing on each of the four sides ties all those columns together so that it acts as if it's one tube acting together.
One of the last great structural inventions came with the tower that Bill is standing on. At 442 meters, the Willis Tower was the world's tallest building until 1996. Its design is called a bundled tube. Essentially, it's made up of 9 towers bound together to create a single rigid structure. But this design has its limits.
This 9 tubes is sufficient for a building of this height at 442 meters, but what if you wanted to go taller? Say you wanted to go up to over 700 meters. Well, you got to make the footprint bigger. But as we do this, we've gone from something that was 3 wide to something that's 5 wide. So you have a huge amount of area, which is difficult to market. And what's more important is that the space becomes very, very deep. In buildings, you want to have views. You want to be able to see out the window. And you can see your occupants would be so far from the views from the skin as to render the building unusable.
To create a taller tower with bright internal spaces, Bill and his team devise a new structural system.
The structural system we use for the Burj Khalifa is the buttress core. Now the core is the center hexagon in the middle of the building, and that's what's used to resist the twisting forces on the building, okay? But it's much too slender to go to such great heights. So it needs to be buttressed. Now the buttresses are the 3 wings that come off, consisting of these walls that go down the corridors. So you can see how this core has been buttressed in 3 directions by the structure going on the wings. To my knowledge, it's never been done anywhere else. And so it's a unique solution to a very interesting problem.
With the buttressed core concept, natural light floods the interior.
We've come up with a solution which allows us to go very, very tall, but it's light and airy on the inside. It's as if you're in a 10-story building rather than a 160-story building.
In SOM's design, the large tower base helps support the huge weight of steel and concrete. Then, as the building climbs, the buttresses step back in a rising spiral. The team then coats the design in glistening mirrored glass to reflect the desert heat and light.
If you were to compare the Burj to an automobile, you'd be talking about Lamborghinis or Ferraris. It's all about performance, and this building is at the highest level of performance.
This quality comes at a price.
The building cost was a closely guarded secret. We heard some general figures that were thrown out. We guessed that it was somewhere in $1.5 billion range, but we weren't privy to a lot of that information. And again, I think the jury's still out.
Making this billion-dollar design a reality will be a mammoth task. The most basic construction materials must be super-powered.
Strength of concrete was key here, absolutely key. And we produced concrete here that nobody produced anywhere else.
The team uses over 25 separate ingredients to create concrete that stays liquid as it's pumped up the building and then turns solid extremely fast. But getting this special mix to set is a massive challenge in Dubai, with temperatures rising over 45 degrees Celsius.
If the concrete is too hot, it'll set instantaneously and you can't even place it. You have to pour at night when the temperatures are lower, and you have to put in ice and chill water in the concrete mix.
To lift this mix up the building, the construction team uses 3 of the world's most powerful concrete pumps. Over 32 months, the pumps deliver 165,000 cubic meters of concrete, enough to lay a sidewalk 880 kilometers long. The team will then top the concrete tower with structural steel. And as this building rockets out of the desert, men and machinery will go to greater heights than ever seen before.
Okay, over the edge.
The city of Dubai is home to 17 of the 100 highest skyscrapers on Earth. But they're about to be dwarfed by a monster. As construction accelerates, the Burj Khalifa is now growing a new floor every 3 days.
The idea is keep the ball rolling, never stop construction at any point in the project until you're finished. The building's handed over, that's it. That's when you can relax.
While this process continues, there is still one fundamental detail to resolve. The architects still haven't decided on the building's final height.
Usually minor things change, and this one, major things changed. We had the foundations went in way before we figured out the final heights of this building.
It's an issue that has to be cleared up, fast. The landmark to beat is the 508-meter-tall Taipei 101 in Taiwan. SOM's original design is just 10 meters higher.
And one of the reasons why we did that is we didn't want to promise more than we knew we could deliver.
But the architects soon calculate that the structure is so strong, it could stand over 300 meters taller.
We kept on making the building taller and taller. And so it actually grew to about 725 meters there for a while. And it stayed there for a while, then eventually grew up to around 800 meters and finally ended up at the 828 meter height.
When complete, the Burj will stand 828 meters above the ground. The question is, are the foundations strong enough to hold it up? Early on in construction, analysis of the ground under the site highlighted a problem.
It's not like, when I worked in New York City, you get good granite there, you go down 4 or 5 meters, you're in the good granite, and that's what you sit your foundation on, the granite itself. Here the ground is top layer of sand, 3 or 4 meters of sand, and you get into weak sandstones, weak limestones, nothing very good.
But science provides the answer. The future of the Burj Khalifa and its entire colossal weight rests on one scientific principle: friction.
There's basically 2 methods in piling. One is end-bearing piles, which is you put the pile directly on the hard rock. That's what can sustain the load. But here we went with skin friction piles, where the weight of the tower is carried on the friction of the pile, the side of the pile.
The foundations of the Burj rely on the super strong grip created between the ground and the sides of each pile. Beneath the tower, the team has driven 192 piles to a depth of 50 meters to support a 3.7 meter thick raft of solid concrete. These foundations must hold up a building that weighs over 500,000 tons. The numbers are so big that the team has to allow for a small degree of settling in the design.
Once we evaluate all the total load of the building, live and dead loads, we expect the foundations to settle about 75 millimeters.
But the foundations should hold. 3 years after breaking ground, construction reaches 512 meters and 141 floors. The Burj is now the tallest building on Earth. To help move materials, the team hires 3 of the biggest construction cranes in the world.
I mean, these are very specialist cranes, actually huge. They weigh 120 tons dead weight. That's a crane itself, and without anything on the hook.
The high wire act of installing the cranes falls to a special group of men. Sharif and his team of crane riggers. These men come from every part of the globe, and many speak different languages. But they have 2 things in common: a strong nerve and an incredible head for heights. Their task is to erect the cranes and keep them working smoothly. All without a single slip.
They never ever lost sight of the ground and the edge of the building, and it was amazing that these people were so comfortable.
The cranes contain an ingenious self-jacking mechanism, so they can grow alongside the rising building. As every new floor is completed, Sharif and his team add another section to the tower support and lift each crane even higher. You need a steady hand to operate the highest construction crane in the world. And one of the few trusted with the task is Mohammed from Pakistan.
I'm on duty for 12 hours, from 7 in the morning until 7 in the evening.
There was a myth going around that the crane operator lived in the cabin, but I think the cabins are too cramped and uncomfortable.
At 700 meters up in the air, Mohammed's crane cab is nearly twice as high as the Empire State Building.
I like heights. They're great for work. If I need to go higher, that's fine. Whatever the height is, God willing, I'll do it.
As the Burj reaches for the sky, it is entering the unknown. And one powerful force is becoming an increasing threat.
The first overall overarching thing is you have to be respectful of the laws of nature, with gravity, wind, and the sun.
And on a super high rise, the most dangerous and unpredictable of these elements is wind.
And when you get to these heights, the dominant load is actually wind load. It's not dead load, which is actually, the weight of the structure and the cladding and so forth. It's not live load, which is the people in the building. That's fairly small. It's actually wind load. You get the wind blowing on the side of the tower, and of course it tends to bend the tower or try to push it over.
No building demonstrates this problem better than the John Hancock Tower in Boston. A masterpiece of steel and glass, 240 meters tall, the Hancock was constructed in the 1970s. But serious problems soon emerged. Even in moderate winds, people inside suffered motion sickness as the building swayed. And over 5,000 glass panels blew out, shattering on the sidewalk below. Only a major redesign saved the tower from demolition. To prevent the Burj from suffering a similar fate, the team tests the building in a wind tunnel. Peter Irwin is one of the world's top wind engineers.
These are various models of different buildings that we've tested in the past. This one here shows some of the unusual shapes that architects are coming up with. That one's being built in China. When we get involved with a wind engineering project, there are 2 aspects that we need to address. First of all, we need to know what are the winds doing in the area that the building is going to be built. Then we also need to know what is it going to do to the building.
Peter and the team calculate that the Burj has to withstand gusts of up to 240 kilometers per hour. But because of its height, this tower faces an added danger.
Buildings, as they get taller and more slender, run into a particular phenomenon in wind called vortex shedding. This is a model of a tall building, and the wind is blowing this way. And what happens with a building like this is that you get vortices peeling off this front corner, first off one side and then off the other side.
As these whirlwinds peel off each side of a skyscraper, they can pull the building violently from side to side. Peter and the team must make sure that this phenomenon doesn't damage the Burj.
There were 3 aerodynamic improvements that were developed as a result of the wind tunnel test. One of them was to improve the shape of these outer buttresses by softening the corner here. Another one was to reduce the width of the tower higher up. And a third improvement was achieved by reorienting the entire tower relative to the prevailing wind directions.
The end result is an incredibly stable building, with a shape that resists vortex shedding.
So you might say that this shape confuses the wind and it's unable to create these strong crosswind forces that affect many other buildings.
The Burj is equipped to handle the strongest winds that strike Dubai. On site, the superstructure is shooting upwards. Once completed, the Burj Khalifa will contain 900 apartments, a 160-room hotel, and 37 floors of offices. The building will use up to 36 megawatts of electricity, enough to power a town of 20,000 people. In a power outage, 5 huge generators will supply backup electricity. But first, someone has to get these massive machines into position.
3 days before Christmas Day, and look what Santa's brought me. That's a 22-ton generator, and there's 5 of them. Pull it. Gently. Keep your eyes on the machine. What have we got? 26. It's supposed to be 22.
Someone, somewhere, has made a critical mistake. Each generator should weigh 22 tons.
Why is it 26 tons? You're amazing. Amazing. Everything is rated below 25 tons. The spreader beam is rated until 25 tons. All these slings, they're 6 tons each, that's 24 tons, and we're trying to lift 26 tons. Therefore, all these people that are underneath this are at risk. Why is that? Right now, my people are at risk.
Yes. It's 26 tons. It's 26 tons.
Yes.
The generator is 4 tons too heavy, and the chains could snap at any moment.
Put it down. These things are not an exact science. It's experience, and I'd sooner not risk the lives of men or machines.
When you're building on this scale, safety is paramount. The team must reinforce the lifting gear before moving the generators into the building.
You go downside, huh? 99.
As work progresses, the task of keeping everything on schedule is taking its toll on David Bradford.
I went all out here to produce the best job possible. That had an impact, obviously, on my family life. My wife didn't see me, although she didn't complain about it, but I'd show up home and my wife had already gone to bed, and I'd be out in the morning before she got up.
But the job's just about to get even tougher.
It's kind of a building you can't afford to make mistakes.
Okay.
That's the bottom line. You make a mistake, the building stops, then everybody incurs huge costs. The contractor's got all his plant and equipment lying idle. He's got thousands of workmen out of work, basically. Can't afford mistakes. You have to check, double check. Everything has to be more or less perfect, all the way up the building.
And with the superstructure almost done, one thing is less than perfect. The glass panels that should already cover most of the building are still nowhere in sight. As the finished shape of the Burj Khalifa begins to emerge from Dubai's desert haze, the team urgently needs to start cladding the building in its steel and glass facade.
As the construction drives upward, you need the cladding to enclose the building, create interior environment where you can actually work inside and do fit out and mechanical work. All the kinds of things that make the building habitable need an enclosure.
It is a massive task to seal the structure from wind, rain and sand. 24,348 individual panels must be assembled and installed on the exterior. But the company commissioned to supply the panels has gone bust. Now the building is in danger of going over schedule and over budget.
Every idle day, every decision is not made, costs somebody a lot of money.
Local contractor Arabian Aluminium brings a new panel supplier on board. And they track down a problem solver to kick-start the operation.
I hopped on a plane, arrived in Dubai for the interview and was taken to the job site. And he said, well, this is the job and this is what you're going to be doing. And I looked up and I said, wow. And he goes, yeah, it's not even halfway there. So big surprise. And I said, well, where's the windows? He said, well, this is a problem. There is no curtain walling. There's no design. We don't have a system. I said, well, this is a job for me then. I can fix this problem.
Construction of the facade is now 18 months behind schedule. To put the build back on track, John Zarafa helped set up a brand new factory devoted entirely to the Burj.
I thought, yeah, it's going to be difficult, but it's a challenge.
We were fairly amazed because they went from appointment of their new contract through design, through production of the components and ready for the testing in a space of 4 months.
This is a typical panel that was used on the Burj, basically with a vision glass, big piece of vision, small vision glass, stainless steel spandrel, vertical bullnose. It's a stainless steel fin, it's mirror finish, which is at the moment has got protection on it, which will eventually get taken off. These panels are literally lifted up as a complete unit and they're hung. That's why they call it a curtain wall. It's actually hanging from the slab above.
Covering buildings in glass might look good, but in Dubai, this creates a special challenge, as John demonstrates.
We've got a piece of clear glass here, just normal glass. The sensors are measuring the temperature in the box to understand how much heat is transferring through the glass and into the box. So if this was on the building, this is the amount of heat that would transfer through the glass and into the building. The outside temperature is now reading 46 degrees Celsius, which is very, very hot. As you can see, we're having a bit of a sweat.
46 degrees Celsius is high, but that's nothing compared to the temperature under the glass.
The current temperature inside the clear glass box is reading 98 degrees Celsius, so not too many human beings that I know could actually live in this environment.
The internal temperature is just below boiling point. If this ordinary glass were installed in the Burj, the building's interior could become the world's biggest sauna. But the team has a high-tech solution.
Here we've got the glass for the Burj Khalifa, which has 2 coatings on it. The outside coating is a silver coating, which captures the UV rays and reflects them back out of the building. Inside coating is a titanium coating, which captures the infrared rays.
By reflecting infrared and UV rays, the glass drastically reduces the amount of heat that penetrates the building. But this technology comes at a cost.
To everything that is involved with making a panel, to the point of bringing it to the site and installing it, you're probably talking close to $2,000 US a panel. times 24,000 panels, it's a lot of money. So 24,000 times 2,000 is 48 million.
As the glass and aluminium arrive in Dubai, factory workers assemble the panels and ship them straight to the building site. The panels are up to 6.4 meters long and weigh up to 750 kilograms. And every single one must be lifted individually and installed by hand.
It's very dangerous. You can imagine these panels are quite large, and as soon as the wind grabs them, they're like a big sail, so very difficult to control. The panel could go flying back into the building, the glass would break, and you're going to get a shower of glass coming down the building. A guy could get his legs cut open and stuff like that. It's quite dangerous.
As the workmen seal the building, no one is following progress closer than construction manager David Bradford.
The major milestone, believe me, been working on this thing for a year now. It's been a nightmare. On a Friday, if I wasn't coming into work, I'd set my telescope up on the roof and spy on the cladding contractor to make sure he was working. If he wasn't, I'd give him a telephone call. Yeah, hey, what happened? You know, why aren't you working?
We actually recovered all the time that we needed to get the building back on track, which was really astounding that they were able to do this.
The curtain wall is virtually finished. 5 years after breaking ground, the Burj is racing towards completion. On the outside of the building, one of its signature features is taking shape. The highest external balconies in the world.
It was a client's suggestion, and my first thought was, you better bolt down the furniture.
We'll head into the main control room.
Wind engineer Peter Irwin has a simple way of demonstrating the problem. Using a state-of-the-art wind tunnel at the University of Ontario, run by engineer John Comar.
The air is streaming through this side. It contracts right through this nozzle in a very uniform fashion and streams right into that corner number 1.
Okay. What we want to do today is to look at the effect of wind on people. We will presumably be able to have them harnessed down to be safe.
We'll certainly strap them down and get them linked to the floor so they don't blow away.
In Dubai, the Burj Khalifa might be hit by winds gusting up to 240 kilometers per hour. And this demonstration will show the effect of high winds if an ordinary person was standing on an unprotected balcony.
Okay, we're turning on the wind, Simon. It's going to go up to 70 miles an hour, so get ready.
Okay.
in case you run into trouble.
130 kilometers per hour is equivalent to a Category 1 hurricane.
Could you try and take 1 or 2 steps forward? Okay, thank you. That's enough.
It looks like to be on a balcony in that kind of wind at 120 stories.
To prevent people being blown off the Burj Khalifa, the architects developed ways to protect balcony users from the wind.
We came up with these glazed balustrades which keep the wind from blowing straight through across the balcony terraces. We came up with these architectural dividers which keep the wind from coming over the balustrades and sweeping across the surface of the terraces. And we created these trellises which stop the downdrafts from pushing down over the tops of each terrace.
But inside is the most ingenious solution.
Well, we have wind alarms installed on every facade where there's a terrace. So if the wind speed on the terrace exceeds what we consider to be safe for the occupants, there will be an alarm that goes off to warn people not to use the terrace at that particular moment.
Meanwhile, further up, the building has yet to reach its final height. The construction team must crown the structure with one of the most extraordinary pieces of engineering ever attempted. A 136-meter tall steel pipe, weighing over 350 tons and measuring just 1.2 meters across at the very top.
The spire, to us, seemed to be the culmination of the building. How do you take this tapering tower and end it? If you chopped it off, it would look truncated. So we thought it had to stretch all the way up into the sky.
But there's a huge problem. How to lift the spire and place it on top of the building.
The thing is that we couldn't get the crane high enough up to set the spire. Even with the crane at maximum boom height, it couldn't get anywhere near the top of the spire.
No crane in the world can handle this job, and no helicopter can lift 350 tons of steel. It seems the spire is too big, and its destination too high. But then, an engineer suggests an ingenious solution. Lift the spire in pieces and assemble it inside the building.
The spire was basically constructed inside the shaft of the building, and then using strand jacks, it was then jacked out of the building.
All the lead architects and engineers gather to see the spire rise into its final position.
Here we are for the last jacking of the spire to take it up to the top.
It's a pretty nice moment to see this happen.
For the first time, the silhouette of the Burj is complete. The team can now start to apply the finishing touches. This building doesn't just have to be the tallest in the world, it also has to be the best. And to make sure it's just that, some brave men are about to go to extraordinary heights.
It's a long way down here.
That's it.
Long, long way down.
After an incredible team effort, workers are finally installing the last curtain wall panel on the Burj Khalifa.
The key to the job was the planning. We planned that whole thing down to the millimeter, down to the second.
The race is now on to finish the building before it opens in 3 months. After 6 years of construction, it's covered in dirt and dust. But there's a simple solution. Teams of window cleaners will polish the entire facade by hand and rope. All 24,348 panels. 800 meters up, there's one more job. After dark, the entire building will be illuminated by thousands of decorative lights. But at the tip of the spire, the last 7 lights still need to be installed.
The scope of work was to cut 7 holes into the existing spire. If it was me, I probably would have said, Out of 2,000 lights, 7, forget about it. Standing on the ground, you're not going to notice. But AMAR wanted to do this job 100%. You know, they set their targets very high.
The construction team must find a way to finish the job.
You couldn't get a scaffold up there. The crane couldn't get that high.
Rope access expert Mick Flaherty has the answer.
The immediate reaction was, are you crazy? You know, I mean, how do you intend on doing this by hanging on a rope?
Mick recruits a highly trained supervisor to lead the job.
Now this is an abseiler. This is a guy that's worked in the rope access industry for many years.
But just before they're due to start, disaster strikes.
At this height, it does something to you. You know, you're totally out of your limits. Making our way into the spire, I could see it in his eyes. He was concerned. He went white. He stops and he says, I'm sorry. I says, what's wrong? He says, I don't want to put my own life at risk. I can't do this job.
With no time left to find a replacement, there's only one solution. Mick has to lead the job himself. It's a highly dangerous task, in some of the toughest conditions imaginable.
For me, it was the heat. It was the environment here in Dubai. You know, it was a heavy construction job in an extreme environment.
It's too dangerous and inaccessible for a TV crew. But Mick films it himself. First, inside the spire, the team cut 7 holes in the 55mm thick steel.
Woo! Oh, the back 7! Yee-haw!
Job very well done, Melcher.
Yeah, thank you.
Job very well done, Hector.
Yeah. Woo!
He's going to get into position now.
Then, Mick has to seal the lights in place from the outside.
We got to the top of the spire and I rigged the job up and threw the rope and looking to make sure I had knots on the end of them.
This one's a serious one.
Yeah.
Okay? Very serious.
You're all ready now?
All ready, sir.
Okay, over the edge. It's a long way down here.
Yes, sir.
A long, long way down. You feel so high, you know? It doesn't feel real.
Okay, Jamil.
Yes, sir. All okay, sir. All right.
Put it there.
That initial going over the side and doing the abseil, it was just a mega buzz. It was like, shall I look down or not? We've been cutting the hole with the steel. We've then been installing the light housing. And now we're going to finish by sealing. Automatic, yeah?
Yes, sir.
So that is the job complete.
These guys, they have bodies of steel. Isn't that right, guys?
Yeah.
See? This is what it's all about. Appreciating your job.
The Burj Khalifa finally opens to the world in January 2010. Standing 828 meters high, it is the world's tallest tower by over 300 meters. Creating it took the combined effort of tens of thousands of people. From the hardest workers and the toughest bosses to some of the brightest minds in the architectural world.
It was a great feeling to get the job. It was even a better feeling to finish it. And you can see the result over there. I mean, it really is a fantastic building.
Okay, done.